through Chapter 2. Gee, I didn't mean for that to rhyme. Anyway, this is going to be a review of reasoning and proofs. We did some two-column proofs. I admit we didn't do as many as you would think, considering the topic is reasoning and proofs. But we're going to do two-column proofs throughout the rest of the course, especially in triangles. Yes, we're going to do much more with congruent and similar triangles and things that you don't know too much about yet, but you'll be experts by the end of the course. So let's start reviewing. We're just going to do a whole bunch of problems, which will use what we learned in Chapter 2. So let's go. Well, speaking of two-column proofs, we're going to solve for a particular variable. Notice we have one equation with two variables. So we can solve for one variable. We can't actually get a numeric answer, not unless we put a number in for a or h, but we can go back and forth. Right now, we already have h. In other words, we have an equation that solves for h in terms of a. What they ask us to do is solve the formula for a. So how would you do this as a two-column proof? And normally, I think you can say that the solution to almost any algebraic equation can be written in two-column proof form. You have a sequence of steps which you justify at each point. That is basically a two-column proof. Remember, the statement goes over here, just write yes, and the justification. They frequently say reason. That's possible too, I guess. I like justification better. I don't know why. Just what I'm used to, I guess. So what do we do first? How about we get the a separate here. We got it inside parentheses with the 4/5 out front. So first thing we need to do, of course, which in my sloppy way of doing things I frequently don't do because it's already written there, is write what's given. That is 200 minus a. And the reason is given. That's an h. Wow. There we go. H equals that stuff. That's given. Okay. That means h equals 40 times 4 is 160. That's 4/5 of 200, right? Minus 4/5 a. And we don't even need parentheses anymore, do we? Take my word for it. We don't. And that is the distributive property. Now, do a little rearranging. What do you say we just add 4/5 a to both sides and subtract h from each side? Which will give us 4/5 a equals 160 minus h. And that, how did we get by with that? That would have been the additive property. I added 4/5 a onto each side, and I added minus h to each side. So I'm going to we did two things, and I'm going to we put it together into one step and call it the additive property of equality. Okay. One more thing to do. Multiply through by 5/4. That'll give us a. Now we could multiply through and put it back into this form with two separate, or we could put it back into this form. In other words, 5/4 of 160 is going to give us back 200, and this will be 5/4 h over here. Or we could also do this. Since this is the way it was given to us, I don't see anything wrong with writing the final equation. equation this way. Although there's also nothing wrong with writing it all out. And how do we get by with this? Well, that was the division property of equality. So, not too many steps, fairly easy, and the fact is solving any algebraic equation can be done this way. It's kind of it's not very efficient that way, but it's good practice. Now what do we need to do? To find a bowler's average with this. Oh, the average score with a handicap of 12. Okay, so H is the handicap. A is the score. No, I didn't use S. Oh well, I guess A is for average. All we have to do is plug 12 in here. We can do that over here. And average score would be 5/4 times 160 minus 12. Is that 148? And so, according to this equation, his average score must have been 185. I'm assuming everybody knows what a handicap is, although I don't know why I would assume that. I mean, my father played golf, so I knew when I was a student what it was, but I think there were lots of students who don't play the kind of socialistic sports that use handicaps. That's right, I think handicaps are socialist. I mean, if you're better, you're better. If you're worse, you're worse. What's this? Football doesn't. The inferior team doesn't get to start with 2 touchdowns. Same with baseball, hockey, every legitimate sport. The score is what it is. If you got beat badly, you got beat badly. That's the way it goes. And if you're consistently worse than your competition, then you're probably in the wrong league. But then, who cares? So let's suppose that you're playing some handicap sport. And the way that works is golf is one of the few professional sports that actually allows a handicap. Wait a minute. No, actually, even in the professional tournaments, I don't think they allow a handicap. It's not part of your actual score. When you're playing for money, you don't get a handicap. But for instance, in golf, the idea is to get as low a score as possible. So if you have like a 3 handicap, after you've finished, they'll subtract 3 strokes from your score to improve your score. That's to even things out if you're playing against somebody who's much better than you. Kind of like weight categories in boxing, I guess, but it's not really, because weight categories don't necessarily imply that a boxer is better than another. It just implies that he's heavier and might be able to take a punch or deliver a punch differently. Now, handicaps are supposed to be a way to even things out so that an inferior player can actually beat a superior player with an inferior score. In other words, I know that's crazy. If I had a big handicap, I could get a lower score than the man I'm playing with and still beat him after we factor in the handicap. Now, if that's not socialist, what is? So the last question here, now that you understand handicaps, or at least my explanation of what handicaps are, your teacher might have a different explanation for handicaps. There's more than one way to look at these things, and they are pretty popular. I can't stand them, but most of the people who play sports seem to think they're okay, so what do I know? I'm a math guy. Now, is it possible to calculate a handicap for a bowler with an average score above 200? Well, I mean, you can look at the formula here. Suppose he averaged 300. By the way, if you don't know anything about bowling, 300 is the maximum. I'm talking about in real scores. Handicaps mess everything up. Who knows what the maximum is? You can work out all kinds of equations and try to change reality if you want to. But an actual real score maximum is 300. So suppose your average score was 300. You would be like Superman, I guess, but in theory, suppose it was. What would that mean? Well, first it would mean you were a monster on the bowling alley. But second, your handicap would look like 4/5 of 200 minus 300, which is minus 100. That's minus 80. Is that impossible? Well, I don't know. I mean, like I said, handicaps are kind of silly to begin with. So what's the limit on silly? Why can't you have a negative handicap? If your average score is 300 and then you bowled 300 in the tournament, your adjusted score would be 220. I don't know whether that's legitimate or not. If you're willing to accept handicaps, then why not accept negative handicaps? You add minus 80 to the score, that reduces it. So what would happen is if you're below 200, handicaps get added to your score. On the other hand, if you're above 200, handicaps could get subtracted from your score, which would tend to put all the scores right in the middle. I don't bowl in any leagues. I haven't done it since I was a kid, so I don't really have any idea whether they allow for negative handicaps in bowling or not. Mathematically, it doesn't seem ridiculous to me. And socially, well, socially, I'd say any handicap seems kind of ridiculous to me. So you'll have to decide whether these negative handicaps make sense or not. Maybe the whole class can discuss the whole concept of handicaps. See what you really think about them. Now here we have the results of a survey. For the rest of your life, if the current crop of surveys is any indication, you're going to get hit with some survey about every week or two, depending on what business you're in. If you go into education, you're going to see a new survey about 3 times a week. Other businesses maybe less often. But there's something to keep in mind about these surveys. They were asked what form of transportation they use. Well, how do you know they told the truth? I used to make stuff up on my surveys when I was a kid. I didn't care. You want information, go get it yourself. Why should I answer your questions? So I never have much confidence in surveys where they ask people what they did. Plus they left some things out. I used to hitchhike to school. I don't see that listed here. Oh well, it's another survey for us to play with. Just don't take these surveys too seriously, that's all. Not these, not any. Does the statement about 1,500 students attend Porter High School? Does it make sense, considering the data? Well, how would you interpret this? Number one, to answer this question, you have to assume that there's a certain mutual exclusivity in transportation modes. That is to say, they are mutually exclusive. You don't take a car, a bus, a school bus, and walk all in the same trip. But I guess you could. I mean, you could take the car to one of those, what are they called? Places where you can go park and ride, that's right. I don't know if they have them everywhere. But some of the more urban areas have parking rides where you drive your car to a place where a public bus picks people up. You could take a public bus from the parking ride to a place where the school bus picks you up. Or you could take public transit to a place half a mile from where the school bus picks you up, walk there, and then take the school bus. Possibly you could take all 4 forms of transportation. If we assume they only do one of these, that means that, and every student actually answered the question, and answered the question only once, That's another thing I used to do, is grab a piece of paper and respond like 5 times. Yeah, I was kind of a jerk in school. It's not something I recommend, it's just what I did. So what do we got here? We got 400 and 400 is 800. 200 is 1,000, and 2 is 1,200. Well, I don't see 1,500 out of this. Maybe I'm reading it wrong. Is there something up here that would indicate that less than all students responded? All students in the high school were surveyed. Well, see, there's another ambiguous statement. Survey means they were asked. Who knows if they responded or not? If we're going to believe that we collected a questionnaire from every single student, then it seems to me there's about 800 plus 400, which would be 1,200 students. After all, 400 took public transit, 400 walked. I seriously doubt that statistic. 200 took the school bus, and 200 took a car. So I would say that this doesn't follow from the data. I would say that assuming nobody turned in a survey twice, there are at least 1,200 students. Other than that, you don't really know what's going on. About 1/3 of all students at Porter take public transit. Aha. Well, 1,200 responded. 400 take public transit. Well, maybe we should do it the other way and see what fraction of students took the bus. And I'd say that equals 1/3, doesn't it? And what was the question? About 1/3 take. So, yeah, I would say the data does support that statement. John makes the conclusion that Porter High School is located in a city or a city suburb. Aha. Well, I think this is probably why he would make that assumption. It's really just you can draw that conclusion because cities and urban areas tend to have public buses, trains, whatever, lots of public transit. You get into more rural areas, you find little or no public transit. This would not even be an option. The last school I was teaching at, there was 0 public transit. It would have to be one of these 3. That's all there was. There wasn't even, I don't think you could even find an Uber or a taxi out there. It was just, you got yourself there, or you took the school bus. And it was pretty much that way with everything. Except for the school bus, of course, because school buses only go to schools. You want to go anywhere else? You can drive your own car, you can walk, or I guess you could hitchhike. That was it. Now I would say that was a deductive conclusion. We don't have, well, I mean in a sense we're reasoning from these examples of what people have done. But we're actually using deduction because we're reasoning that there isn't much public transit in rural areas. And with that many students using public transit, he's probably not in a rural area, which puts him in an urban area. And that's deduction. Now, what about Betty? There are twice as many students who walk. Well, there are 400 who say that they walk anyway. And again, who knows? And 200 who are willing to admit that their parents drive them to work. Actually, a lot of high school students drive their own cars to work, don't you? Well, I'd say that made perfect sense. And I would say that was also deductive reasoning. It's not a matter of looking at a bunch of examples and then extrapolating out and saying, well, it must hold for this case too. It's a matter of simple numbers. 400 walked, 200 drove. 400 is twice. 200, I would call that deductive reasoning. And this problem was all just about interpreting a diagram. Those are pretty easy, and they're real easy to practice too. There are plenty of examples in your book that'll have diagrams. And you don't have to knock yourself out with like 3 pages of equations to get to an answer. You can look it over and pretty much explain to yourself what you think the answer is, and then check and see if you're right. Now here's one that, well, it's part of one anyway. I think I left something out here. Okay, now we're going to use a whole bunch of words, a verbal description, to create a diagram, a visual representation of this paragraph. Usually the easiest way to do it is just one step at a time. Well, when I say visual representation of this, I guess I mean this whole thing here, not just this paragraph, but everything that's listed here. We will produce a visual diagram based on all these words. Okay, so there's a meeting, all these people will be there, and here's all the words that tell us where everyone's going to sit. We'll put a P up here for principal, chair 10. Why not? The senior class treasurer will sit at the other end, so let's put a T here for treasurer. I'm just making this up as I go along and hoping that I don't run out of letters. We'll see what happens. The senior class president will sit to the left of the principal. Well, let's see if the principal was sitting here and facing this way. That would be his left, wouldn't it? And we'll write CP for class president. Now here's how I would do it, one step at a time. Principal will be in chair 10, so we'll put a P right there for the principal. The senior class treasurer will sit at the other end, so there's ST for senior treasurer. Senior class president will sit to the left of the principal. Well, the principal is sitting there, I guess he'd be facing that way, unless they turn around their seats, but I'm going to assume that everybody's facing inward towards the table, and that'll put the senior class president right here on the principal's left, next to the junior class president. Well, there's only 2 seats next to any given seat. This one's already taken, so that means the junior class president has to be right there. So he's next to the junior class president, but directly across from the sophomore class president. All 3 treasurers will sit together. You have to wait a minute before we put those in. Let's get some more information first, because at this point we've got this guy, this one, and this one. That leaves us 3 seats here. It's tempting to just throw some treasurers in there, but we've already got one down here. So that means the treasurers could be here, here, and here, 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 and here, or here, here, and here. We don't know yet. So we'll have to do some more reading. The 2 sophomores will sit next to each other. Okay, there are only 2 sophomores in the meeting, and we already determined where one of them is. He's in seat 9, directly across from the senior vice president. And he can't be over here because that's the principal's seat. That only leaves 1 spot. So that's where we put the sophomore vice president. Okay, what about the two vice presidents? And the freshman treasurer will sit on the same side of the table. Well, there's a vice president. The treasurers all have to sit next to each other. Also, all the vice presidents and the freshman treasurer have to be on the same side of the table. We already know where one of the vice presidents have to be. That means the other one's got to be either here or here. If we put the vice president here, we could put treasurer here, here, and here, if that works out according to the rest of it. But for now, I'm going to put the senior vice president here and the freshman treasurer here. That puts them on the same side of the table. We know where the senior treasurer goes. The treasurers all have to be next to each other. There's only one spot left for the junior treasurer. Now once we've done all this, we've accounted for everyone in the meeting except the secretary. It's down here. Secretary will attend. And there's only one seat left, so we put it here. So taking it one step at a time, and just, it's like following instructions for lighting a gas heater. You know, pull this knob, turn the other knob a quarter of a turn, push the other knob back in, whistle for 3 seconds, light a match, hold it for 1.5 seconds, push knob B in again, rotate knob C another quarter of a turn, hold the match near the gas line, and watch everything blow up. Same thing here. Explain why the senior class secretary must sit between the junior class president here and the junior class treasurer. Well, I think we already did that when we were laying it out. I mean, if you didn't understand that, then you wouldn't lay it out right, would you? And we figured out why. Because the freshmen had to be on the same side as the vice presidents. That put the freshman treasurer here. We're given that the senior treasurer is here. They all have to be next to each other. That puts the junior treasurer there. And we already figured out the junior class president had to be there because he has to be next to the senior class president, who is to the left of the principal. And only leaves one spot for the secretary. Now, can the senior class vice president sit across from the junior class president? Well, I don't see how. It says right here, the senior class president will sit to the left of the principal, next to the junior class president, and across from the sophomore class president. And here it says he's sitting across from the junior class president. I don't know which mathematical principle to point to, but I don't believe you can sit across, directly across, from more than one seat. If you're in this seat, that's the one you're directly across from. Like I said, I can't tell you which postulate says that, but I believe it. I hope you do too. Which means the answer is no. He could not sit across from the junior class president. He has to sit next to him, because that's also given right in here somewhere where it says that he's going to sit next to him. So you'd be violating the statements that were given if you put the senior class president and the junior class president directly across from each other. And here's a pretty simple one, which is just fairly simple reasoning. I guess that's what they intend you to practice here. You can check them. Sometimes with these even and odd things, if you see something like that in a standardized test, it's not a legitimate proof, but if you want to know if you're right or not, just pick an odd number and stick it in there. 1 and 3 are both pretty good ones to pick because they're small and easy to work with. And the thing about this is, if it's true for one odd integer, it's going to be true for all of them. Especially if you just pick something like 3. So 3 and 2 is 5. That's not even. 2 times 3 is 6. Might as plus 1 is 5. Well, that's no good. 3 times 3 is 9, plus 1 is 10. Well, that could work. 3 times 3 is 9, plus 2 is 11. So I would say C. And if you don't like doing it that way, you can just recognize that two odd numbers, the product of two odd numbers, is always an odd number. Two even numbers, or an even and an odd number, comes out even. Two odd numbers comes out odd. Add one to an odd number, and you've got an even number. So either way, it'd be pretty easy. Aha. Now here's where we're going to use some inductive reasoning. For instance, which number is in, let's start with something we have, or something a little bit simpler. In other words, see, we got 2314, 2314, let's carry it out. I'm not going to go out 300 places. Let's see here. Now, what's in the 10th place? Without counting, what would your guess be? Well, it repeats every 4, right? So, for instance, if you wanted to know what was in the 7th place, what would you do? You'd probably throw out the first 4 and figure out what would be in the 3rd place. You said, what's in the 5th place? You'd throw out the first floor. Pardon me. Throw out the first floor and you're on the 2nd floor. You throw out the first 4 and the 5th one would just be the first one in the next set of 4. In other words, what you're going to do is throw out every complete set of 4. That makes sense, doesn't it? Throw out every complete set of 4. And then start counting for more you got left, assuming you don't have complete sets of 4. In other words, what's 4 divided by, what's 300 divided by 4? For instance, in this case, 300 is evenly divided by 4. That means we have 75 sets of 4 in 300 terms, or 300 digits, pardon me. So the 300th digit, since it works out evenly, will just be 4. It'll be the last digit in the set of 4. If this isn't making any sense to you, think in terms of time. When you've got, say, 850 minutes, well, that's some number of hours in minutes. How many minutes would that really be once you've written it in a form that most people would recognize? So if you have 850 minutes, what would you do? In hours and minutes, you would divide by 60, right? And 6 goes into that 1, 2, it's actually 1, 4, not 2, pardon me, with some stuff left over. It doesn't go evenly into 850. So if we multiply 6 by 14, what do we get? It's 24, 6 and 2 is 8. And this really should be see if I can set a record for mistakes in one problem. It's 60 times 14, which is 840. Dope. What we're doing here is figuring out how many of the minutes are accounted for in hours. In other words, we have 14 hours here. That's 840 minutes with 10 minutes left over. So we could write this 850 minutes as 14 hours and 10 minutes. And you're totally familiar with that by now. And that's all we're doing over here. We're just recognizing the cycle. It cycles every 4 digits. How many cycles are there? And what we do is just get rid of all of the cycles and figure out what's left over, just like we did here. How many cycles of 60 are there? There are 14 cycles of 60 in this. That works out to 840. We get rid of those and we got 10 minutes left over. So in terms of hours and minutes, what is the 850th minute? It is the 10th minute. Same thing here. That's what we're doing here. No difference. And here we're going to use the diagram, just like we did before, to set up an algebraic equation. And again, it's another combination of geometry and algebra. We need geometry to recognize that these two angles are a vertical pair. Vertical pairs are congruent, which means their measure is equal. So we can set up the equation. 3x plus 31 equals 15x minus 5. Now, if we subtract 3x from each side and add 5 to each side, we get 36 equals 12x, or x equals 3. Did they ask us to find the value of these angles? No. They only wanted x this time. If you've got time, it's a good idea to put the answer you got back in. If these two turn out to be equal, and you didn't make any mistakes, like I frequently do. What do we got here? 9 and 31. Well, I'd say that was 40. What do we got over here? 45 minus 5. Well, I'd say that was 40 also. So I think we got x right. It's 3. Down here, okay, we've got 3 lines intersecting. What is the value of x and y? Oops, pardon me. What is the value of x plus y? Well, this is almost too easy. I bet you can spot this right off. What do we have here? Well, first off, this is what we call a straight angle, right? And we have it broken up into 3 angles: x, something else, and y. We know from the additive property of angles that these 3 angles have to add up to the whole thing, or 80 degrees, or pardon me, 180 degrees. So we can immediately write that x plus y plus something we don't know anything about yet equals 180. We know that. However, these 2 lines are intersecting to form a vertical pair. We've got a vertical pair here, which has this line going through it. We also have a vertical pair here. Vertical pairs are congruent. Congruents have equal measure, so this one must be 20 degrees. If we stick a 20 in here and then subtract it from each side, what do we end up with? And you're done. You just needed to spot the vertical pair. And remember, this is a straight angle. It was all pretty easy, right? Okay, let's try this. R is the midpoint of PQ. Well, in these two, they gave us a diagram. This one, I think they expect us to go from words to diagram. We just got a bunch of words. So let's draw a picture here. Let's draw a bad picture, but we got Q here. We'll say, maybe I shouldn't put it there. Maybe I should put it way at the end, down here. If we have to extend it, we will. Although if we extend it over here, we're going to be in trouble. Well, we won't be, but I will. You'll be fine. So here we have segment PQ. Might as well draw that first. They gave us to it. Or, pardon me, they gave it to us. R is the midpoint. It's the midpoint because they say so. If S and T are the midpoints of PR and PQ, aha, respectively. So PR, S is the midpoint of PR. T is the midpoint of RQ. Didn't misinterpret anything here, did I? Points of PR and RQ. Okay. ST, that's this one here. This length here, that's 20. What is PET? Well, this doesn't seem all that tough. Remember, this is a bisector, or a midpoint, pardon me. That means PR and PQ are equal. So let's just write that down. What the heck? PR, and let's not talk about the segments, let's talk about the lengths. So let's just say that they're equal, not congruent. Length of segment PR is equal to the length of segment RQ. We know that. In fact, we know that RT is half of RQ. RS is half of PQ, but they both have the same length. So, we know that RS equals RT. And added together, they equal 20. So, since they're both equal, we could write, say, 2 times the length of RS, or RT, it's pretty arbitrary, equals 20. And that should tell us that the length of RS equals 10. There we go, RS. Well, these two are equal. So RT is also 10. We already know this is 20, so that's cool. What about this here? This is the part we need to know to figure out the distance from here to here. Well, we know that this is half of the distance from here to here, and we also know that it's 10. So this here must also be 10. The distance from here is 10 and 20, which is 30. And actually knowing that this was 10 turned out to be irrelevant. We didn't need that. We just needed to figure out that this was equal to 10 over here, and then recognize that SR, or RS, happens to also be equal to PS. And what we've done here is cut it in half, and then cut the 2 halves in half, which means we have 4 equal quarters. That's all we really did here. It sounded a lot more complicated than it really was. Here's one where we're asked to draw a conclusion from the given information. Well, the conclusion and the hypothesis have some problems right off the bat. First off, I'm not sure if they mean all soccer players wear shin guards. I mean, it's like the general you, whoever you are, or if it's intended to be a specific you, such as you're the person reading it, so it means you particularly. Like in this case, I'm reading it, so it means me as a soccer player would wear shin guards. That's ambiguous. But let's suppose they mean you in particular. You're the one reading this, so they mean the particular you. doesn't say anything about your friend, does it? Or anybody else. No, it doesn't. So, right off the bat, you would say, no, this is just has nothing to do with anything. It doesn't really say much of anything. Suppose you rewrite this as all soccer players wear shin guards. In other words, if you're a soccer player, this is like the general you now. All of you people who are soccer players wear shin guards. Your friend is wearing shin guards, therefore she is a soccer player. Now, there's something you can sink your teeth into a little bit more, because this is a job for the Venn diagram. Whenever you see stuff like this, it's not easy to recognize, not always anyway, if you don't do it a lot. It's a containment situation. Like, which set is the bigger one? Which contains the other one? Is everyone who wears shin guards a soccer player? Or do all soccer players wear shin guards, or do all shin guards wear soccer players? Would be another way to look at it. If you're a shin guard, are you definitely wearing a soccer player? Or could you be wearing some other type of athlete? So if you draw yourself like any kind of a closed curve, it doesn't have to be a good circle, luckily. And suppose this is all people who wear shin guards. Just write shin. Shin guards. This is everyone. Now, there's another circle in here of soccer players. If you're part of this group of people who wear shin guards, you might be in this group of people who play soccer. However, you can fill this with lots of other athletes. Lots of people wear shin guards. They might not even be athletes. It might just be people who get kicked in the shins a lot. So I would put a definite no, this is not a correct conclusion. And as I say, if I was going to do this, if I saw this on a test, first thing I'd do is probably draw a Venn diagram and get a visual picture of what we're talking about here, because some of these get a lot more complicated than this. And if you draw yourself a diagram with the larger inclusion as the larger circle and the smaller one, it makes it easier to reason these out. And keep in mind, it's not always a total containment situation. For instance, baseball players, you could put them in like this, because the catchers would be over here inside the people, this set of people who wear shin guards. On the other hand, most of the players would be out here. They're not wearing shin guards. It doesn't have to be a complete inclusion. And then of course there's out here, or you've got, say, athletes like golfers who don't wear shin guards. Well, describe the pattern in the numbers. Might be easier to start down here. It's not immediately obvious to me that -4, or let's forget the negative signs temporarily. It's not immediately obvious to me that 48 times 4 is 192. On the other hand, 4 times 3 is definitely 12. Spot that pretty quick. 4 times 12 is 48. So we see a pattern of, as we're going down this direction, dividing by 4, except that the signs are alternating. But we can solve that problem if we just keep dividing by -4. Divide 192 by -4 and we get -48. -48 divided by -4 is going to give us a positive 12, and on down the line. So the next number, of course, would have to be -3 divided by -4, which would be 3/4. That's pretty easy, right? The trick was just spotting that you're going up, you're multiplying each one by 4. Negative 4 in this case, because they alternate, which might have caused you to pause for a minute and wonder what the heck was going on. There's another way we could write this, just for fun, just to show it to you. Suppose this one is some other number, which would be 192 times 4. And what number would that be? If we went 1 out this way, this would be negative 768. So how else might we have written this? Well, suppose I did this. 768 divided by negative 4, which is the same as minus 1/4, right? Okay. And what's the next term? Well, I would say it's 768 times minus 1/4, because that is 192, times minus 1/4. That drops us down to minus 48, doesn't it? And what's the next term? Well, minus 1/4 minus 1/4 times minus 1/4. That's our third term here. That's 12. This should be minus 768. Minus 768. Minus 768. Now we've got our signs going in the right direction. What I first wrote would have been minus 192 plus 48 minus 12 plus 3. Put the minus sign in here, and we've got it the way they wrote it, which is what we're supposed to want. Well, you see something going on here? We can kind of rewrite this. It's 768 times, now we have to, well, this is going to be a sequence of minus 1/4 to some power, depending on which term we want. The first term is to the first power. The next term to the second power. The third term would be 768. So the ith term is minus 768 times minus 1/4 to the I. Why did I bother with all that? Well, because you're going to see it later on. This is 1/4, it's some fraction to a power here, either the summation or the sequence. Those are both very common. You're going to see them a lot later on. And this is kind of where they come from, stuff like this. Doggone it, I said kind of again. This is where they come from, period. No kind of about it. Sorry. Now, luckily, these points are all in one plane. Why is that lucky? Because drawing multiple planes is difficult for me because I am like zero artistic. But I can draw one plane okay, I guess. They're all in one plane. In fact, since it's all the same plane, we hardly even need to draw it. But you take a shot at it. Let's pretend that's a plane there. Okay, that's the plane. And they're all in this plane. A, B, and F are collinear. Now, let's draw them that way. Here's F, B. Yeah, I guess we'll put A at the end. Maybe we'll have to extend it, we'll see. A, B, and F. The line through AB is perpendicular to the line through CD. Okay. There's a line through AB somewhere in here. and it's perpendicular to CD. Where is CD? The line through CD is perpendicular to the line through EF. Now there's one line through AB. 2 points define a line. So I actually drew a segment here. Thought that's what we're going to be dealing with, but let's do it right. Now we have the line that goes through points A and B. Okay, so far. That line is perpendicular to the line through CD. Well, let's just draw a perpendicular line to AB. It doesn't have to be between AB, so let's draw it there, and we'll put our little right angle thingy in there to show that this, even though it may not look perpendicular, it is. At least it's supposed to be. And this is CD. Now, C or D could be the intersection here, or they could be out here. We don't know yet. So we're just going to call this CD, but we don't know where the points are yet. In fact, it's actually a line. Okay, so this is line CD. It's perpendicular to the line through AB. And it's perpendicular to the line through E and F. CD is perpendicular, which means what would be perpendicular to this? Well, it would be a line that went this way. So here's one example of a perpendicular line. Well, if it's perpendicular to a line through EF, there's the point F. Now we draw a line that contains F and intersects CD, and any way we do it, it's not going to be perpendicular unless we stick to the line that goes right through AB. If this is the line they're referring to, when they say it's perpendicular to the line through EF, then E must be on this line here. Otherwise, and it turns out it didn't matter where we put CD. There's C, and there's D. So they ask which 4 points must lie on the same line? There we go, A, B, F, and E. And it's just a matter of reasoning your way through it, one step at a time, and recognizing what these words mean in terms of a picture that you're going to draw. And unfortunately, it just takes practice. I can't give you a quick, easy way to always do it, but if you practice doing it, you'll get faster and better at it. Okay, here's another one that's just a bunch of words, and you have to find a way to make sense out of it. This is actually a good problem because you'll probably have to do this someday. And you see these people who can't work on certain days have all these special requests. I can't do this on this day, and I can't work on that day, and I can only work every other Wednesday, and all that kind of stuff. If you ever have to schedule employees, you'll find this is actually pretty easy compared to the real life situation. You're going to get so many, oh, I have schools on Monday nights, oh, except on the third Monday, then we meet on Tuesdays, and on and on and on. And you're going to have to get yourself an Excel spreadsheet and lay it out with all your employees and try to figure out who's working when. Coming up with a schedule that works for everybody is close to impossible. But they're giving you an easier one here. But this is the kind of thing that you might as well get used to because you're probably going to have to do it someday. Now, which way should we do this? We could mark the days that they can work, or they could mark the days that they can't work. I'm going to put X's for a day that they can't work. And just leave it blank If it's blank, the assumption is they can work that day, no problem. So let's start with Jen. What can she do? She can work any day except every other Monday. Well, now we've already got a problem. See what I mean? We can't just cross out Mondays. On the other hand, we can't just leave it blank either because she can't always work Monday. So I'm going to use a single diagonal line to indicate there are some Mondays when she can't work. This is much simpler than what you would really have to do, because if you were really scheduling this, you'd have to have a much bigger sheet that would show exactly which Mondays she could and could not work. Every other Monday and Wednesday, so she's available on some Mondays and some Wednesdays, but you can't count on it. Just lay it out that way. Kim can only work on Thursdays and Fridays. Wow. That means she's out Monday, she's out Tuesday. No Wednesday, but she does work on Thursdays and Fridays. Cool. What about Lou? He can work on Tuesdays and Wednesdays. Well, but he can't work any other day. Okay. So we'll cross him out for Monday. He can work Tuesdays and Wednesdays, but we got to cross him out for Thursday and Friday. What about Mike? He doesn't work on Fridays, but everything else is open, and it's always the same Friday. If this guy works for you, you'd probably like him. He's easy to schedule. At least you always know which day he's not available. Nina cannot work on Tuesdays. Okay, another nice one. She's only got one day when she can't work, and it's always the same. The question is, name 3 tutors who can work on any Wednesday. Well, here's Wednesday. All you have to do is look across and see who's open. Boom. Lou, Mike, and Nina. In fact, there are only 3. If there were 4, you could just pick 3 of the 4. But no, because they say any Wednesday. They even italicize it just so you wouldn't think they mean sometimes on Wednesday. Who can occasionally work on any Wednesday. That doesn't even make sense, does it? Sometimes I can work on any Wednesday. So the 3 open spots give you your answer. The key to this was just laying it out. I mean, you can see that once you've laid it out correctly, your 4-year-old cousin could come up with the answer here. He could tell you the answer. But he might not make up this chart. We'll leave that for the high school students. Well, that's the end of the Reasoning and Proofs review. Next, we're going to study parallel and perpendicular lines. And I know that up until now it's all seemed kind of abstract. Some of you might say totally useless. And so far, it hasn't been real exciting. There hasn't been a whole lot that would probably get you a cup of coffee anywhere. But some stuff is coming up. In Chapter 3, we're going to do some things that, if you learn it, you could actually pick up a couple of bucks doing it. We're going to learn about slopes. Those are used in simple things, such as floor plans. If you are managing or own a business, you will frequently, well, maybe not frequently, it seems frequent if you're actually doing it, submit plans to the Department of Planning and Development every time you make a change. You want to add a sink somewhere, even though it's a pretty simple thing to do, you have to submit a plan to the Department of Planning and Development and a floor plan that shows where everything is and where it's going to be after you make the changes. Some of the things you'll have to include in that floor plan is the slope of stairways, ramps, driveways. If the parking lot is not perfectly horizontal or flat level, it has a slope to it. You'll have to compute that slope and include it in your floor plan. So we're getting closer and closer to things that you would actually do and use at home or a few bucks doing. Floor plans, heck, if you figure out how to do floor plans for people, you can always find somebody who's got better things to do than make up a floor plan, and he'll pay you to do it for him. These are business owners, so it's not like they're broke and can't afford to pay you decent money. You can pick up a few bucks if you understand what's going on. Chapter 3 will be the beginning of your ability to pick up a few bucks using math. Seriously, you can do that. There's tons of people who need someone to help them just occasionally with things that they're not very good at. Either they don't follow instructions very well. Most of the time they just didn't pay too much attention in high school, so they have to find somebody like you or me who did pay attention. You can pick up a few extra bucks. It's a good deal. And that's what we'll be doing. Oh, next time, I forget how many videos it'll cover. 5, 8, something like that. But we're getting closer and closer to really useful things.